Ok, adesso stiamo registrando. Ok, vedete la slide in full screen?
Sì.
Okay, so we can start. So let me recap just the very few considerations that we did yesterday at the end of the previous lesson. So the standard model has received a very strong experimental confirmation, and it is indeed able to describe with very high precision almost all the known phenomena in particle physics, and now also including the neutrino oscillation after the introduction, the more recent introduction of the PMNS matrix into the theory framework. And also the recent discovery of the Higgs boson in 2012, of course, constituted the final proof of the theory. Now, as we also noticed yesterday, despite the huge agreement between standard model prediction and experimental data, the standard model cannot be considered the ultimate theory of particle physics. And there are many reasons, some of which are really fundamental. Let me just highlight the most important. So first of all, the standard model does not include gravity, okay, which is already a big problem. Then, as we saw yesterday, it requires 25 free parameters. This means free parameters that cannot be constrained by the theory itself, but they have to be put by hand somehow and measured experimentally. The standard model does not provide a mechanism for the generation of the neutrino mass. As I was mentioning yesterday, neutrino mass cannot be generated by interaction with the Higgs field. In fact, there is no interaction between neutrinos and Higgs field as far as we know. And also, the standard model cannot explain the observed matter-antimatter asymmetry in the universe, another big issue. And additionally, it does not provide any candidate for the dark matter, which constitutes something like 23% of the universe content, and even more, cannot explain what the dark energy is, which add up to something like 72% of the universe content, and many more others. Okay. So, as a result of these, since decades, theoreticians have been working hard to develop a new and more general and fundamental theories that, of course, have to include the standard model as a low energy limit. And in parallel, the experimentalists have been searching for signals of new physics in the last decades, so new particles or new interactions that, of course, cannot be explained in the framework of the standard model. And we possibly have already few hints, as we discussed this year during the course. So we saw that the G-2 experiment this year announced the 4.2 sigma level discrepancy with the standard model concerning the muon anomalous magnetic moment. And just a couple of months ago, the LXCB presented a 3.1 sigma level discrepancy with the standard model concerning the lepton universality violation. And there could be even more signals. So today we will try to discuss very briefly, okay, without going into any detail, what is beyond the standard model, okay, and what are the ideas trying to interpret new features. So let me start with dark matter. So as I think you all know, it is an established observational fact that big fraction of the matter of the universe does not emit electromagnetic radiation. Does not emit light, okay, in simple words. And so it appears dark to us, and this is the reason why we call it dark matter. However, its existence is indirectly probed through the gravitational effects in the interaction with the visible matter, so the matter that emits electromagnetic radiation, such as stars, galaxies, galaxy cluster, etc. In particular, the most clear evidence of dark matter in the halos of the spiral galaxies derives from the observation of the revolution speed of the stars, those that are in the periphery of the galaxies, as a function of the distance from the galactic center. So let me consider as an example this galaxy, okay, spiral galaxy. So the assumption is that the majority of the mass of the galaxy, so the majority of the stars, are concentrated into this central spherical bulge, okay, with the radius Rs. And then there are, of course, a minority of stars that are distributed all around in these spiral branches. And by assuming these, then one expects that the tangential velocities of the stars should be proportional to the distance for the stars that are located inside the bulge here, and should go like 1 divided by square root of r for the external stars, so those that populate these the branches of the spirals, spirals, yes. Okay, here rho is the average density of the star within the bulge. So this is the naive expectation in absence of dark matter. Well, this is the way you would expect stars would move around the center of the galaxy. And so, in other words, in the peripheral regions, when the distance is larger than the radius of this central bulge, the velocity of the stars should decrease as 1 divided by square root of r. However, what is found is something completely different. It is actually found that the velocity at larger distance are much higher than predicted. Okay, and the observed velocities are actually consistent with the mass distribution, which increases with the distance. So there is more matter outside than inside the galaxy, something which is, of course, astonishing, because we cannot see it, okay, but it is probably there. So let me give you some more quantitative example. So again, this is our spiral galaxy. The red line here is the expected distribution of the velocities of star as a function of the distance from the center of the galaxy, without assuming dark matter, so only considering the visible matter. However, what is measured is this distribution here, which is completely different and remains essentially flat as long as we increase with r. And you see also experimental actual observational points here. Okay, so this is the distribution that you would expect only considering visible matter. And if you want to account for all this data here, you have also to introduce a halo around the galaxy, which contains some non-visible matter. So this is pretty much the situation. The halo is much larger than the galaxy dimension itself. Okay? So there must be a large contribution from non-visible matter in the halo galaxies that allows to explain these large velocities of the stars in the peripheries. But this is not the only way to have hints of dark matter. There are other independent confirmation now based on large-scale structures, so a cluster of galaxies, and also from the gravitational lensing effect. I guess you know what gravitational lensing is. That's in a very few words, suppose that there is a galaxy very, very, very far away from us, and then between the galaxy and us, there is some very massive object, like a galaxy cluster. Then the light coming from the faraway galaxy travel, of course, towards us, but they are deflected by the mass of this intermediate large system, heavy system, because of the curvature of the space-time. And so, essentially, we can see the galaxy that is beyond the galaxy cluster, because the light is distorted by the curvature of the space-time. And actually, we see fancy patterns like rings or things like that. Now, of course, the gravitational lensing then is also an indirect means to test the quantity of mass that is around the visible cluster of galaxy. Okay. So, in particular, cosmological models for the formation of galaxy and cluster of galaxies indicate that this structure could not be formed without the presence of dark matter. Okay, so the dark matter is actually essential also to allow the formation itself of galaxies and galaxy clusters. Now, the fact that about 23% of the universe is filled with dark matter and about 72% by dark energy, as you probably know, is one of the most remarkable results of the precision study of the anisotropies in the cosmic background radiation, especially thanks to the two satellite experiment, WMAP first, and then Planck more recently. So this is a map of the universe obtained by the Planck satellite, which essentially represents the universe as it was 380,000 years after the Big Bang. So essentially at the time where the first atoms could be formed, because the universe was now cold enough. And so, starting from this point, the light was free to propagate. Now, today we observed a cosmic background radiation at the temperature of 2.7 Kelvin, which is very well described by a black body radiation at this temperature, corresponding to a wavelength of 2 millimeters. But of course, this is the result of a red shifting from the original, much hotter distribution at 3000 Kelvin, okay, at the time where all these photons were released after the formation of the first atoms. Now, if you look at the map, you see that there are, of course, these anisotropies in this temperature distribution, and these anisotropies are actually very, very tiny. We are talking about something in the order of 20 microkelvin. So it is an effect of the order of 10 to the minus 5 compared to the absolute value of the temperature. And these anisotropies were originated by quantum fluctuations. Now, the crucial point here is that there's a temperature anisotropies corresponds exactly to the primordial density fluctuation from which galaxies started to evolve. Okay, so all the structure that we see today in the universe are essentially a result of quantum fluctuation occurring in the very early stage of the universe, which then evolved into, let's say, density fluctuation, and then, of course, thanks to the gravity, object started to be formed. Okay, so part will be attracted, etc. Now, these satellite experiments are very crucial. Okay, because from the observation of these temperature anisotropies, one can really learn a lot about the structure of the universe and actually about the content, the energy content of the universe. Okay, so by global analysis of the WMAP, Planck, and also the precursor experiment COBE, today we now have a clear, rather clear picture of how matter and energy is distributed in the universe. So in particular, we know that the baryonic matter, so the one that we can explain with the standard model, is overall 5% of the total. And in particular, only 5 per mil is the visible baryonic matter, so star, galaxies, galaxy cluster, etc. And essentially 4.5% is the non-visible baryonic matter that we describe later. Then there is a huge contribution, as I was saying, 23% by non-baryonic dark matter. So something that it is there, it is probed through its gravitational effects, but it is not standard baryonic matter, so it is not made by standard model particles. And these, however, can also include neutrinos, so to a certain extent. And then we have this dark energy, okay, which is essentially 72%. Dark energy can be somehow understood as like a negative pressure gas, something really strange to understand. So such that the density remains constant as the volume increases, okay? Something really outside our standard knowledge of thermodynamics, for instance. And it is responsible for the acceleration of the expansion of the universe, okay? As it started something like 5 billion years after the Big Bang. Now, so we have a lot of information thanks to these temperature anisotropies, but none of this information tell us what is dark matter made of. What is the nature of dark matter? So there are, of course, many options. For instance, the non-visible baryonic matter, let me go back here to this second item here. So it is matter that essentially is not emitting light, can be constituted by remnants of dwarf stars or neutron stars, or even giant planets like Jupiter or black holes. All these objects essentially do not emit light, or they emit in a narrow electromagnetic range. And but they are massive. Okay, so somehow they contribute to the mass balance of the universe. And all these objects are classified as machos. Now, the point is that if you now sum the masses of all these objects, so the total mass of the machos is completely negligible compared to the amount of the dark matter that you need to explain the dynamics of the stars and of the galaxies. Okay. So the machos, which are made by baryonic matter, so standard matter, cannot for sure explain the anomalies in the, for instance, in the motion of the stars in the periphery of galaxies, etc. So we need something much more abundant in the universe. And most of the non-baryonic dark matter, so what we really don't know what it is made, could in principle be made by a gas of a weakly interacting particle, where weakly means indeed through the weak interaction that we know, which can be further divided into two categories. So the so-called cold dark matter, which is made by heavy non-relativistic objects, or the hot dark matter, which is made by light and relativistic particles or objects in general. And the distinction between two, of course, is not necessarily trivial, but there is a sort of threshold that one can fix around 1 keV. So for masses that are beyond 1 keV, they should be relativistic, so they should be hot dark matter, and if you have above, then you are slow and hot, and all the cold dark matter. Give me a moment. Sorry for a moment. Ok, scusate, non sono del campanello. Okay. Now, there is an exception, however, from this scheme that is represented by the axions. So axions are non-relativistic but ultralight particles, supposed to be particles. I mean, they have not observed so far. So with a mass of only 10 to the minus 5 electron volt. Okay, so these axions are not observed so far, but are predicted by some models beyond standard model. And in principle, they are interesting objects because if they do exist, they can be detected through their conversion into photons when passing through a non-uniform magnetic field. And there are also, as you probably know, experiments ongoing in many laboratories around the world, and one of those is also carried out by one of our colleagues in Ferrara. Now, let's now focus on the cold dark matter, so on the non-relativistic component of the dark matter, and these candidates are usually denoted generally as WIMPs, which stands for weakly interacting massive particle. So they interact weakly through the weak interaction, but they have also to be very massive. And the most accredited WIMP candidate at the moment is the neutralino, which, as we study next today, is the lightest stable supersymmetric particle with a mass in the range from 100 to 1000 GeV. Now, how can we detect WIMPs? So there are two different approaches, the so-called direct searches and the indirect searches. So let me start with the direct searches. So direct searches of WIMPs are based on the measurement of the recoil energy of atomic nuclei after scattering elastically with a WIMP crossing the detector volume. So suppose you have a volume filled with some material, then somehow a WIMP crosses the fiducial volume, the sensible volume of the detector, and so it makes elastic scattering with one of the atomic nuclei. Okay, then the atomic nucleus that is involved in the process, of course, will get some recoil energy on the order of a few keV, so very, very tiny energy. And if your detector is good enough, so has a sufficient high energy resolution, then you can, of course, detect this recoil energy. Okay, and so have a signature of this kind of processes. So the extremely high energy resolution needed to achieve such kind of measurement can only be possible through new generation of so-called cryogenic calorimeters, or bolometers, which are able to detect indeed the tiny increase in temperature which is generated by the ionization or the excitation produced in the detector material by these very small recoiling energies of the nuclei. Of course, the background due to ambient relativity is extremely high for such kind of measurement because essentially one is looking for really a few signal events per year, if any. Okay, we don't even know if these WIMPs exist. So it is, of course, of crucial importance to suppress the ambient background. So first of all, to work underground, under the mountains and in the mines, to shield from the cosmic rays, and also you have to use ultra-pure materials in order to avoid the contamination from ambient radioactivity. There is a question?
Yes, I wanted to ask, if we're looking for this type of signal, can you see this with neutrinos or already particles we know to calibrate?
For the WIMPs, you mean?
Yes, I mean the equivalent, because this type of signature you could get with neutrinos, I suppose, or.
Okay, so the direct searches are this kind here, as I just described. So you look for small recoil energy for the nuclei. The neutrinos, as we will see in a moment, will take a place in the indirect searches of WIMPs. So I will show this in the next slide. Of course, I mean, detecting neutrino is always a challenge. Okay, so you need a huge flux, and you will be able to measure only a few of them if you're lucky, because the interaction is very weak and very rare. But I mean, this is somehow exploited in the indirect searches, as we will show in a moment. Now, there is in a way a smart trick that has been used by the DAMA experiment in Gressasso, still looking for these direct searches of WIMPs. And the idea of the DAMA experiment is the following. So suppose that our galaxy is surrounded by a halo of dark matter, in particular a halo of WIMPs. Then our solar system, as we know, it is moving at the speed of 200 kilometers per second around the galactic center, so across this halo of dark matter. And so, in principle, the solar system should be continuously hit by a wind of WIMPs. Okay, we are just moving through them. And the idea of the DAMA experiment is actually that this effect is increased when we are in summer, because in summer the velocity of the Earth adds up with the velocity of the Sun around the center of the galaxy, whereas in winter, so in December, the two velocities are in the opposite direction, so you have to consider the difference. Okay, so in other words, the idea is that in summer, so around June, we should expect an increase of these events because we are going faster through these halo of WIMPs, if it exists, and a smaller effect should be observed in winter because we are moving slower. Okay, so the velocity are subtracting in that case. And this is what indeed the DAMA experiment published. So here you see the data collected over 7 years, and the data indeed suggest the presence of this annual modulation with recurrent maxima in June and minima in December. Okay, so here you see the years 2004, 5, 6, 7. So it is 7 years of measurement, and you see these very nice seasonal modulation. Okay, over time. So I mean, this is very, I would say, impressive. Okay, but other experiments using different techniques have not seen this effect. Okay, so they do not confirm. And in particular, there is this Anais 112 experiment as an underground experiment in Spanish, who published just last week. Okay, this was last week. The preliminary results using now the same technique of DAMA. Okay, so the two experiments are really comparable, and they see no annual modulation at the significance level of 2.7 sigma. And of course, this is not a really huge significance, but the significance will increase in the next years. In particular, we expect a significance larger than 3 sigma by the end of the next year. Okay? So at the moment, the question is still open and under debate. Now, as I was saying, there are also indirect searches for the WIMPs. Okay, and this is where indeed the neutrinos can take place in this game. So the idea is the following. We know that WIMPs, by definition, are massive and can also be actually very massive, okay? And so they can be gravitationally captured by celestial bodies, such as the Earth or the Sun or whatever. And under gravitational attraction, the WIMPs will move towards the center of the Earth or towards the center of the Sun, where they accumulate, okay? Now, if you have an enough amount of WIMPs and anti-WIMPs, in a small volume because of this accumulation, then it is also possible that WIMP anti-WIMP annihilate. Okay, and this can occur, for instance, in the center of the Earth or in the center of the Sun. And in this kind of annihilation process, indeed, neutrinos can be produced. For instance, you see a WIMP anti-WIMP annihilating through the weak interaction, so by emitting a Z boson, which further can decay into neutrinos, for instance. Okay. Clearly, the Z can decay into any charged pair of charged particles, but these are, of course, immediately absorbed by the Earth or by the Sun. but neutrino can escape. So in principle, we can exploit this by catching these neutrinos coming either from the center of the Earth or from the center of the Sun. And this is indeed the idea. Of course, now the neutrino can be catched in a Cherenkov detector, okay? So it interacts with some nucleus through the weak interaction, it produces a muon, and then the muon is detected indeed through the Cherenkov light. There is another possible candidate for the dark matter, which is the so-called sterile neutrino. This is a neutrino which does not interact via weak interactions. So we know that the standard model neutrinos, electron, muon, and tau, can only interact through the weak interactions, okay? Suppose now there is also a different kind of neutrino that does not even interact with the weak interaction, and this is indeed, for instance, the right-handed neutrinos that we know that they could not take part to the weak interaction and so to the standard model. So indeed, right-handed neutrino, if they do exist, they can be sterile neutrino, and if they are massive enough, they could play some role into this dark matter business. However, one has to say that cosmological constraints make it quite unlikely that the light sterile neutrino can be the main component of dark matter. So this sterile neutrino with masses of the order of a kiloelectron volt or even above could in principle be accommodated in the present theories, but with some difficulties. Okay, so this brings us now to the theory of supersymmetry. So supersymmetry, you probably have heard about, is one of the most studied theories beyond the standard model, given the possibility to test it in principle at the Large Hadron Collider, because it is a theory that works at the TeV scale. So in principle, at reach from our Large Hadron Collider. Now, in general, a supersymmetric transformation is a transformation that changes by 1/2 the spin of the particles, while leaving unaffected, so unchanged, the electric charge and the core charge. But if you now change the spin of a particle by 1/2, you are transforming a boson into a fermion and a fermion into a boson, right? Now, fermions and bosons in this theory can then be considered as the members of a more fundamental multiplets. However, supersymmetry does not allow to relate the existing standard model fermions and bosons to each other. So indeed, for this theory to work, we need a real new family of supersymmetric particles that we call sparticles. We add an S on top of them. And so we need this to discover this new family of particles, and at the moment, none of those have been observed at the Large Hadron Collider or at any accelerator experiment. Now, how this supersymmetry works. So in supersymmetry, each standard model particle has a super partner, which, as I said, differs by 1/2 a unit of spin. So in other words, the super partner of each spin 1/2 fermion would be a spin 0 scalar bosons that we call sfermion. So quark and lepton, as we know in the standard model, are fermion with spin 1/2, and the supersymmetric partners that are called squarks and sleptons are now scalar bosons, so with spin 0. What about the gauge bosons? Also here we have to swap the spin. And so our standard model gauge bosons, the photon, the Z, and the Ws, which are spin 1/2 objects, which are vector bosons, are now a supersymmetric counterpart, which is now a spin 1/2 fermion. And these are called the photino, ziino, and vuinos. Altogether, they're called geuginos. And here you see essentially what you would need in order to fill the spectrum of the supersymmetric theory. So we have particles from one side and the supersymmetric particles, so the supersymmetric partners from the other side, okay? So these are essentially the particles that we know from the standard model, but for each of them, by shifting the spin by 1/2, we obtain now the supersymmetric partners, okay? So we have the squarks, the leptons, and the geuginos here. Photino, vuino, ziino, guino, gravitino. Now, why don't we have observed this object yet? Well, there are two reasons. First of all, because maybe they just don't exist. We don't know. or because they are too heavy to be produced at the Large Hadron Collider. So particles are predicted to be indeed heavier than particles. So the expected mass are in the range between 100 and 1000 GeV. And obviously, since particles and sparticles have different masses, the supersymmetry is a broken symmetry. Okay, this is much like the SU3 flavor symmetry for the quarks, which is a broken symmetry because the mass of the strange quark is much higher than the mass of the up and down. Okay, it's more or less the same reasoning. On the other hand, if the supersymmetry were an exact symmetry, the masses of particles would be the same as for particles, and so sparticles would already have been discovered, which is not the case. Now, in the minimal supersymmetric model, it predicts the existence of 4 Higgs bosons, okay, 2 of which are neutral and 2 are charged. And so we call them capital H10, H20, H1 plus, H2 minus. And this is the mass hierarchy, okay? So the first neutral is the lightest, then we have the second neutral is intermediate mass, and then the charged Higgs are the most massive. And the lightest of these 4 corresponds to the standard model Higgs, the one that has been discovered in 2012. Now, the super partners of the scalar Higgs field are, of course, now fermions, spin-1/2 fermions, and they form weak isospin Higgs-Sinus doublets. Okay, so plus 0, 0, minus. There has to be always a difference in charge of 1 unit of electron charge. So we have, in this case, 2 weak isospin doublets of supersymmetric Higgs bosons. Now, an interesting thing of supersymmetry is that the 4 neutral fermions, so the photino, ZeNO, and the 2 neutral Higgs bosons, and also the 4 charged fermions, so the VUinos and the 2 charged Higgs bosons, are not mass eigenstates. They do not coincide with the mass eigenstate. And we know already from the quarks and from the neutrinos that when this happens, then of course the physical states are given by superposition or mixing of the mass states, right? This we have learned already in several examples, already in the standard model. So indeed, the corresponding mass eigenstate, which are respectively called the neutralinos and the charginos, are mixing of them. So we have 4 different types of neutralinos, or with a neutral electric charge, which are the 4 different combinations of these 4 neutral fermions, and then we have these 2 charginos, which are this different combination of these 2 charged fermions. And of course, all these objects have no correspondence in the standard model. In many supersymmetric models, such as the minimal supersymmetric model, there is a new conservative quantity which is called R. So it is the so-called R parity, which is -1 to 3 times the baryonic number plus the leptonic number plus twice the spin. Okay, so you can compute this number for any standard model particle, and you will obtain R equal 1. So there will be an even number, so -1 to an even number equal +1. So R is +1 for all standard model particles, and by swapping now the spin by 1/2, it turns out that this is always -1 for all the superpartners. Now, the conservation of R implies the existence of a stable supersymmetric particle with the smallest mass. Okay, this is what we call the lightest supersymmetric particle, which, being the lightest, is also supposed to be stable. Now, the nature of the lightest supersymmetric particle is still a mystery. Okay, we don't know exactly what it could be, but there are, of course, several possibilities. And if it is the residual of all the decay of a supersymmetric particle from the beginning of the universe, then it should be, of course, very abundant in the universe. And since we didn't find it yet, it must be, of course, neutral and should all interact weakly. Otherwise, we would have already observed it in the past. Now, in many supersymmetric models, the lightest neutralino, so the X10 tilde, is the lightest supersymmetric particle. Okay, and so this is indeed the best, at the moment, the best candidate for the cold dark matter. It is a weakly interacting stable particle, and it is considered one of the most probable candidates for the dark matter in the universe. Okay. In other supersymmetric models, the lightest supersymmetric particle is instead neutrino. So there are still options. Now, this table summarizes again the full picture. So we have the particles with r+1 and the supersymmetric particles with r-1. For instance, we have our fermions, so the leptons and the quarks with the spin 1/2, and this corresponds to the sparticles, so fermions with now spin 0. And these are the names: electrons, muons, taus, neutrinos, quarks. Then we have our gauge bosons sector, okay, which are vector bosons in the standard model, and this turns out to be 1/2 fermion in the supersymmetric world, okay, with these fancy names. And then we have the Higgs sector, so we have to have 4 Higgs sector and 4 supersymmetric partners. These are bosons, scalar bosons. These are again fermions. And then we have the mass eigenstate, which are the neutralinos for neutral particle, combination of neutral particles and the chargino. So combination of neutral fermions and chargino combination of charged fermions. Can we apply the same Feynman formalism for supersymmetry? Yes, we can. Of course, we have to take into account some additional rules. So to calculate the transition matrix for a given process, one has just to consider also diagrams in which particles are substituted by their superpartners. Okay, and then the coupling constants are the same. One has to, however, to take into account that supersymmetric partners are produced in pairs from a standard model particle, and the decay of the supersymmetric particle always contains a supersymmetric particle and a standard model particle. So let me give you some example. Okay. So we know that in the standard model, the W can decay into electron and neutrino, and the photon into a quark-antiquark, for instance. Now, in addition to these, which are the standard model decays, we have now other possibilities. So the W can decay into a pair of supersymmetric particles, okay, electron and neutrino. The supersymmetric W, so the Vuino, can decay in a supersymmetric particle and a standard model particle, either in this way or the other way. And similar for the photon. Okay, so the photon, of course, is in the case in QQ bar. The photino must decay into a supersymmetric quark or particle in general, and a standard model one. So a quark with a quark. And a real photon can decay, a standard model photon can decay only in pairs of supersymmetric quarks. So one can see here, for instance, the result of a plus annihilation that can happen at a plus indeed colliders. So a plus annihilate into either a photon or a Z, and then by what we have seen here, then those two have to decay into pairs of supersymmetric particles, so L plus, L minus, and each of them has to decay into a standard model particle and a supersymmetric particle. Okay, so this is more or less what one would expect as an event topology for creation of supersymmetric particle in an annihilation process. There is also a very nice, very interesting reason to like supersymmetry. Okay, so in addition to provide a good candidate for the dark matter, which is the lightest supersymmetric particle, the supersymmetric theories also are interesting because they result in a much better convergence of the 3 fundamental coupling constants: the strong, the electromagnetic, and the weak. And this happens at a very large energy scale, 10 to the 16 GeV, which is the scale of the grand unified theories. So you see here, for instance, the coupling from the strong force, the weak force, and the electromagnetic force in the standard model, so without considering supersymmetry. And as you can see, there is no any point in this parameter space where they match all together. Whereas if you consider supersymmetric theories, then there is a point at a very large energy, so 10 to the 16 GeV, where indeed the 3 forces converge into one single unified interaction. So how can we now observe experimentally the production of supersymmetric particles? And it is indeed the search for supersymmetric particles is one of the main focus at the high energy accelerators, in particular the Large Hadron Collider. For example, a signature for squark pair production and subsequent decay, so suppose you create a quark pair production, then this decay into a quark pair and into two neutralinos, okay? Then what is the signal that we have in our detector? Well, we would observe two jets from the hadronization of these two quarks, and then a big fraction of missing energy, because of course these two objects will not interact with the detector, and they will escape the detector, carrying away their energy and momentum, okay? So one way to search for these quark pairs is to look for two jets in combination with a big fraction of missing energy. Now, so far, no evidence of direct production of a supersymmetric particle has been discovered. But the search is still, of course, continuing. And as you know, there is now a project for the very far future to build a new accelerator, is an electron-positron collider, still in the region of CERN in Geneva, but with a circumference of 100 kilometers, so much larger than the Large Hadron Collider, with E plus E minus annihilation at the center of mass energy of the order of 100 TeV. So this would push the energy frontier by another order of magnitudes. And of course, the main arguments for building this extremely expensive machine and ambitious machine is, of course, for searching for supersymmetric particles or even other beyond standard model objects that indeed have not been found at the Large Hadron Collider. Now, let's move on to other theories, more general theories. So this is now the turn of the grand unified theories. So in the standard model, as we know, each family of fermions is constituted by two quarks, for instance, the up and down, and two leptons, for instance, the electron and the neutrino. Okay? Although there is no obvious justification for this. So one possible argument could be that both quarks and leptons are different manifestations of a single particle, so that they are essentially members of a multiplet. Now, in this hypothesis, there must be a connection between the strong interaction, which acts only on the quarks, and the electroweak interaction, which acts both on quarks and leptons. Okay, and so essentially a new interaction between quarks and leptons must exist to make this possible. This hypothesis then requires a grand unification of the three fundamental interactions, the strong, the electromagnetic, and the weak, and of course only gravity would be excluded at this level. And in this framework, all the processes are characterized by one single grand unified coupling constant, Gu. Now, an indication in favor of the grand unified theories is this convergence of the three coupling constant, okay, at the energy of 10 to the 16 GeV, which is of course further enforced in case of supersymmetric supersymmetry theory. So if the grand unified theory is also a supersymmetric theory. Now, to incorporate quarks and leptons into one single multiplet, one of course needs a larger symmetry group, so for instance SU5, such to describe the unified interaction at energy above this incredibly high value of 10 to the 16 GeV. And obviously, such a symmetry has to be spontaneously broken, much like the same way the Higgs mechanism break the electroweak symmetry, in order to recover our electroweak symmetry at lower energies. Okay, so if we stay above 10 to the 16 GeV, then possibly we have this unified theory with an SU5 gauge group. But then, when we now go to lower energy, so below this threshold, of course, we have to recover our standard model gauge group. Now, the grand unified theory symmetry requires two additional gauge bosons, which are called X and Y, and with incredibly high masses. So the masses are the order of 10 to the 15 GeV. Okay, so extremely high. And those bosons will then generate the transition between quarks and leptons, and so violating the baryonic number and the leptonic number. Okay? We know that this kind of transition are not possible in the standard model because the baryonic number and the leptonic number are conserved always in the standard model. But if you go beyond, then we also have to allow for this possibility. And these two gauge bosons indeed could allow for quark to lepton transition, so violating simultaneously the baryonic number and the leptonic number. Okay. Clearly, at energy well below this threshold here, these processes are, of course, heavily suppressed. Now, what is one of the consequences of the baryonic number violation and leptonic number violation is that then the proton can decay. Okay, so if we allow, as we mentioned already quite some months ago, at the beginning of the course, to that the baryonic number is not anymore conserved, then it is possible that the proton decay into a pi0 positron. And you see here 4 different diagrams where this can happen through the mediation of these X and Y good gauge bosons. Okay, so for instance, here the exchange of a Y boson, okay, allowed to transform a quark into a positron. Or here you have this kind of annihilation that provides at the end a lepton from here. Okay, and this is indeed the reason why it is so important to look for the proton decay, because if, which is now being searching, for instance, at Super Kamiokande, because if you do observe some very rare but still significant events of proton decay, then this means that the baryonic number and leptonic number has been violated, and this can be well interpreted within these grand unified theories. Another consequence of the grand unified theory is the creation of supermassive magnetic monopoles, okay, that appeared at the time of the breaking of the good symmetry, so in the very early universe. So this presumably occurred when the universe was only 10 to the minus 35 seconds old, so only very, very tiny fraction of time after the Big Bang, when the temperature was order 10 to the 28 Kelvin, corresponding indeed to the scale of the good, so 10 to the 15 GeV. Now, the mass of these hypothetical magnetic monopoles is somehow related to the mass of the X and Y bosons, divided by this unified decoupling constant, alpha U, okay? And it turns out that if they exist, their mass should be of the order of 3 10 to the 16 GeV. Now, the existence of magnetic monopoles, of course, is something really awaited, because this would repair the apparent asymmetry between electric charges and magnetic charges. We know that we can isolate electric charges, plus or minus, but we cannot isolate magnetic charges. Okay, this we studied already in general physics. Now, if these magnetic monopoles do exist or have been really created in the very early stage of the universe, then this symmetry is now established, or was established at the time of the early universe, 10 to the minus 35 seconds. However, it is still a broken symmetry because the value of this charge is very different. So the value of this magnetic charge isolated would be something like 2 orders of magnitude larger than the electron charge. Now, magnetic monopoles have long been searched, but not found yet. And there is another additional important implication of goods. So, these grand unified theories include processes which violate baryonic number conservation, and these, in addition to a small CP violation, such that the X and Y bosons might produce a slightly higher number of particles than antiparticles, all these together could well explain the observed matter-antimatter asymmetry in the universe. So searching for goods is also extremely important because this would solve this fundamental problem. So at present, goods are the only theories able to explain the observed extremely small ratio between the number of baryons and the number of photons in the universe. Okay, so they are very, very appealing, although they are, of course, very, very different, very, very difficult to be probed experimentally and observationally. Now, what about gravity? So far, we neglect completely about gravity. Let's now put gravity into the game. So gravity becomes relevant only at really microscopical scales, and only at energy of the order of the Planck mass, which is 10 to the 19 GeV. So it's 3 orders of magnitude beyond the root scale. And this energy corresponds to spatial dimension of the order 10 to the minus 35 meters, okay, which is the Planck length. And such incredibly high energies only, of course, could exist in the very, very, very early stages of the universe. So times shorter than 10 to the minus 43 seconds after Big Bang. Okay, so you can imagine how short is the. Actually, I cannot imagine. It's too short. How short is this time interval? Now, a quantum supersymmetric theory of gravity, which is called supergravity or simply SUGRA, based on a local gauge invariance, has been proposed, which is, of course, very appealing. The theory, however, is incomplete and presents some conceptual problems. Okay, and in certain SUGRA models, the light supersymmetric particle is instead the gravitino. So we have one more additional candidate for explaining the dark matter. Now, the graviton, okay, as you know, it is thought to be the gauge boson of the gravitational interaction. It is supposed to be massless and a spin-2 particle, so a tensor particle, tensor boson. And it's supposed to be the mediator of any field theory which includes gravity. Now, why spin-2? The reason for the spin-2 condition is required because of the fact that gravity is only attractive. Okay, so different from, for instance, electromagnetic interaction, which is both repulsive and attractive. Gravity is only attractive, and this feature can be only obtained if the mediator is a spin-2 particle. The coupling of the graviton with matter is predicted to be extremely weak. In fact, we don't have observed any graviton so far. And indeed, any direct search for detection of the graviton is extremely difficult, if not even impossible. Okay. However, as you know, very recently, direct and indirect evidence of gravitational radiation, so the gravitational waves, have been clearly demonstrated. Okay, in these merging phenomena. Okay, where two black holes or two neutron stars merge together and propagate gravitational waves through the universe. What about then string theories? We are almost at the end. So string theories allow for a relatively simple inclusion of quantum gravity, but at the price of requiring at least 10 dimensions. So 6 more than our ordinary space-time, okay, which is, of course, not trivial at all. The fundamental degrees of freedom for the string theories are not elementary particles, but rather one-dimensional objects, which are called strings. Okay, so we can imagine now the matter to be made in this way. So matter is made by molecules, molecules by atoms, atoms are made by electrons and nucleus, nucleus is made by proton, proton by quark. And now at the very elementary level, so the electrons or the quarks, which up to now are considered the most fundamental object, the most fundamental matter particle, can instead be described in terms of these one-dimensional strings. Okay, and the properties of the electron and, in general, these elementary fermion are, so the mass, the charge, the spin, etc., are essentially are determined by the vibrational modes of these strings. And the interaction between particles, so particle emission and particle absorption, corresponds in this theory to the splitting and recombination of these strings. Now, because string theory potentially provides a unified description of gravity and particle physics, it is clearly the best candidate for a theory of everything, something that was long searched by Albert Einstein, as you know, but it was a failure at the end. So a self-consistent mathematical model that describes all the fundamental forces and forms of matter. We have also analog of the Feynman diagram now in the string theory, which where the Feynman diagram are replaced by these smooth two-dimensional surfaces. Okay, but there is here an interesting point because in the string theory, infinite momentum does not correspond anymore to zero distance, which is our known relation due to the uncertainty principle, right? Instead, in string theory, the approximate relation between distance and momentum is given here. So we have this additional term where now the momentum is at the numerator, and this quantity in the denominator is called the string tension, which is the fundamental parameter of the string theory. And the consequence of this is also important, because the loop integrals over such smooth surface do not suffer from the infinite momentum problem of the integrals into loops in the standard model, the one that at the end led to the renormalization, if you remember, solution. So here in string theory, we don't have these divergences due to this unusual relation between position and momentum. The relation above implies also a minimum observable length, okay, which is one of the square root of this string tension, which corresponds to the Planck length, indeed, 10 to the minus 35 meters, which is the size, indeed, of these strings. According to string theories, gravity appears negligibly weak. Why? Because we probe it from our four-dimensional world. Okay, so we probe only a four-dimensional projection out of the at least 10 dimensions. However, in a full glory 10-dimensional universe, the strength of gravity would appear comparable to that of the other fundamental interactions. And you see here this interesting picture. Okay, so the point is that these additional dimensions, so these at least six additional dimensions, are not accessible from our four-dimensional world, because they are wrapped with an extremely small curvature radius. So for in our scale, this is just a string, but for a hand, you have already an additional dimension here. Okay, so just to tell you that there is an additional degrees of freedom which is tightly wrapped and that we cannot access in our world. Finally, the preons. So one of the characteristics of the standard model, which makes it unlikely to be the final theory, is the presence of three families of quarks and three families of leptons, with essentially the same properties. So the three families are just clones of the first family, but just heavier. Okay, all the other quantum numbers are just the same. So this is not, of course, a good feature for a very fundamental theory. Okay. So the situation is now conceptually similar, indeed, to the regularities that were observed more than 100 years ago in the periodic table of elements, which suggests that the atoms are not fundamental objects, but rather constituent objects, and also to the regularities that were observed in the 60s of the last century, so the famous hadron multiplets, okay, the octet, the decuplet that we studied, which indeed suggested that the hadrons are not elementary particles, but they are made by quarks, so they have an internal structure. And so possibly we can also infer that our elementary fermions are not really elementary, so that quarks and fermions have an internal structure. So we should indeed consider this possibility, and also maybe also the vector bosons are not elementary objects, but are composite objects, okay? The presence of fundamental components of quarks and leptons that are called preons could indeed reduce, as an additional advantage, the number of elementary particles and the number of free parameters in the standard model, okay? Because we will get a description of the same physics, but now using a much smaller number of degrees of freedom, and so of free parameters. Now, a minimal number of two different preons inside a quark or a lepton could explain the lightest family of quarks and leptons, and then the other families could be explained as, or interpreted as, excitations of the fundamental state given by the first family. So let me just tell you how this works. So according to one of the simplest theory of preons, the so-called Rishon model, there exist two elementary particles called Rishons. Okay, then of course there exists a more sophisticated model that uses three preons. So in this very simple two-particle model, we have two Rishons, so two elementary objects, T and V. So the T is charged and comes with a fractional electron charge, and spin 1/2, and V is neutral and still spin 1/2. So now we can combine those two in a proper way to obtain the standard model particle. Okay. So all leptons and quark flavors of the first family are given by ordered triplets of preons, such that each triplet has a spin 1/2 as we want, and such that each particle gets the correct electric charge as we want. So for instance, the positron can be made by 3 T regions. Okay, so you get in total a charge of E and a spin of 1/2. The neutrino, which is neutral, can be obtained by a combination of 3 V regions, so you get your desired neutral charge. And the quarks, up-type quark and down-type quark, anti-quark in this case, okay, can be obtained now by combining 2T and 1V or 2V and 1T regions, okay? And so you get, again, the correct electric charge and by proper combination also the correct spin. In these models, the baryon number and the lepton number are not individually conserved, but rather the difference, B minus L, is the conserved quantum number. Now, since preons have not been found at the Large Hadron Collider, of course, a lower limit of at least 10 TeV can be conservatively set for their masses. So they have to be heavier than, and so this could be the reason why they're not seen at the Large Hadron Collider. Clearly, if they exist, okay. However, if they exist, they should be. It should be possible to observe them in cosmic rays, okay, where we can have interaction as energetic as 100 of TeV, okay, when very high energetic cosmic ray hit our atmosphere. The last word I want to say is about the universe evolution. So this is a very well-known picture of the universe. Everything starts at something like 13.8 billion years ago in the Big Bang, and then things evolved up to today, okay, where we have now stars, galaxies, etc. So let me only focus on the very first stages of the universe. So this picture I already shown you in the past. Let me just go once more through this. So at 10 to the minus 43 seconds, if you remember, this is the age after the Big Bang where the gravity decouples from the other forces, okay? So this is the so-called Planck era, okay? Now, moving ahead, so in a time interval between 10 to minus 35 and 10 to minus 36 seconds, this is where presumably the inflation took place. Inflation is a period of time where the volume of the universe expanded in an incredible velocity, actually with a velocity higher than the speed of light. And so in a matter of a very, very tiny time interval, the volume increased exponentially, the volume of the universe. Then we are now in 10 to the minus 32 seconds, where the temperature of the universe was 10 to the 27 Kelvin. This is now the point where strong and electroweak interaction decouple. Okay, so this is the region of the breaking of the grand unified theories. Then we move on to 10 to the minus 12 seconds, so where the temperature of the universe was now down to 10 to 15 Kelvin. And this is now the scale of the electroweak interaction. So we are at energy of the order of 100 GeV. And this is now where the weak and the electromagnetic interaction decouple. The next step is the first microsecond. Okay, so 10 to the minus 6 seconds. Now we are in an age of 10 to, in a temperature of 10 to 13 Kelvin only, let's say. And this is now the time where protons and neutrons could be formed out of the quark-gluon plasma that was existing previously. Okay. So before 1 microsecond, the temperature and the density of the universe was so high that quarks and gluons were completely deconfined and behaving in the asymptotic freedom regime. Then the universe cooled down sufficiently to allow them to form, for the first time, bound states, which are hadrons, so in particular protons and neutrons. Then, after essentially 1 second from the Big Bang, where the temperature was down to 10 to the 10 Kelvin, the first nuclear reaction started. So we now have enough energy to form the first nuclei, light nuclei, in this so-called primordial nucleosynthesis. Essentially, we started with the proton and neutron, and in a matter of 3 minutes, it was possible to produce a certain amount of primordial deuterium, helium-3, helium-4, lithium-6, lithium-7, and possibly also some quantity of boron, beryllium, and carbon. And then the last step in our story is when the first atoms are formed. So now the universe is cool enough. It is only 3000 Kelvin. This, as we saw, occurred 380,000 years ago. The first electron was captured by a proton to form the first hydrogen atom. Okay, and once 9 atoms are formed, now we have only neutral object from the point of view of the electric charge, which are atoms. And so the photons are not anymore absorbed every time, and so they are starting to move freely, and so to propagate free from this time, providing this beautiful image taken by the Planck satellite experiment. And I think this is all we have, yes. So we are now at the end of the course. Any questions? Comments?
I mean, yeah, just the last one on the perspective to study, the possible models. So basically, even with the current theories, it's only indirect searches that could probe them, right? Because it's in a lot of cases you need levels of energy which are well beyond our reach.
Yes. Sure, you cannot go much beyond what you have today in terms of accelerators. Okay, so we will probably construct this future circular collider, which is 100 TeV, etc. But maybe nothing will come from that, because maybe the supersymmetry are even beyond 100 TeV. One can look actually now back, as it was 1 century ago, to cosmic rays, so before the advent of accelerators, because cosmic rays can provide, or even cosmic events, so neutrinos from extremely energetic events in the cosmos. This can bring probably indirect information on much more energetic processes, and so on the relic of theories that work at higher scales. But there is indeed a very few chance to probe them directly in laboratories. We can probe them maybe indirectly. And if you remember, one of the ways to do so is to search for the electric dipole moment. We discussed this at the end of the QAD chapter. Electric dipole moment is something that you can test in low energy accelerator. You don't need to go high in energy. But if you find some signal of non-zero EDM, then this is clearly a signal of new physics. Because standard model predicts a very, very tiny amount of EDM.
Because for the cosmic ray, I remember a number, it goes up to 100 TVs or something like that in that range, right? Or...
Yeah. Hardly you can go beyond that, yes. Well, no. 1 moment. No. The energy of a cosmic ray can be well beyond that, actually. I think that the most energetic for something the order of, no, I don't remember, something 10 to the 19 electron volt, if I'm not wrong. I have to check this. Of course, the flux of these extremely energetic cosmic rays is extremely low. Okay, so indeed you need a very large area detector in the Earth, looking for Cherenkov light into the atmosphere and revealing a particle in a large area, like the Auger experiment in Argentina, for instance. So okay, this cosmic ray can go really beyond 100 TeV. Yes. I don't know how much beyond, but probably, yeah. To some extent, yes.
Okay, thanks.
Any other question? Curiosity? Domande logistiche su esami e cose varie? Ne abbiamo già parlato un po' ieri, però se avete ancora domande approfittatene ora, ma sono sempre disponibili ovviamente via mail per dare chiarimenti. Ok. Interrompiamo qui, sto interrompendo la cosa. Allora, interrompo la registrazione. Ok, se non ci sono altre domande, altre questioni, buone vacanze, buono studio e ci incontriamo poi quando sarà il momento di fare gli esami. Okay?
Grazie, arrivederci.
Arrivederci, buona giornata.
Grazie, arrivederci.
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 Arrivederci.